molecule, and it has to be at absolute zero. Did we start? Oh, I was going to wait until after this slide, but thank you, because I probably would have forgotten anyways. We're good. Anyway, this system would have to be at absolute zero because this is the only way that we could get zero disorder. Otherwise, there's no such thing as zero disorder. If any particle motion exists, then it's not zero disorder. There will be some amount of entropy there. So that's kind of what I'm getting at down here. If the temperature increases from absolute zero, starts going up, even if it's a little bit, then the particles are going to start to move around and they won't be in a perfectly orderly arrangement anymore. So this is what it would mean to be zero entropy. Every other substance, every other form of matter has some amount of entropy. Yeah.
So, but you said like from last year, like absolute zero, it's like you could never reach absolute zero.
That's right.
So does that mean that this isn't even?
It is theoretical. Really, it's fictitious. Yeah.
Okay.
So every substance, every form of matter that we know of has some entropy. That's what I'm talking about there. So this is not describing an actual substance and set of conditions. It's just fictitious. Yeah? Okay. And you should know this. When you look at the thermodynamic table, you'll see that more complex, even solids, you can compare solid entropies. The ones that have the most molecules in them, the biggest, most complex, they have more entropy than the simpler ones do. Yeah, I think so. I think somebody will figure it out. Yeah. I think it. I think it could.
I just think you probably did it if we're on Mars.
I
I don't know why.
Isn't it almost like you just get smaller number, like you don't get
You don't get to zero.
You just get smaller. Kind of like how
Yeah,
a fraction. You can only get smaller.
Albert Einstein said that once you get close to absolute zero, everything loses its volume. It just all crushes together. Yeah. And they have evidence for that. Like a black hole. Yeah. 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 That's what they think, is it becomes like a singularity. Yeah. Yeah. Yes?
Would a black hole have energy?
No. That's quantum.
Wrong
That's
class,
quantum.
Daniel, wrong
Oh,
class.
we're
Yeah,
not.
let's not.
Let's not go into
That's
quantum.
just in
Please.
Yeah. Give yourself some time in asking that question.
High class.
All right. Does anybody know what substance, what very well-known substance, has the lowest entropy? Maybe at room temperature?
Water.
No, there's something that's lower than water. The most order, the least entropy, meaning the least amount of disorder. Think about what substance would have the least disorder. Daniel, what do you think? No, it's not mercury. No.
Hydrogen.
You guys are, no. It's got to be a solid, because solids are the most orderly. The most, or the least disorder. I hope I didn't say it wrong before. What is, no, Glenn, not glass. No. You're close.
Sodium.
It's diamond.
What?
Diamond. Diamond is as perfect of a crystal as we know of. Yeah. It's expensive. It's very hard. It's a bummer that it's so rare because they like to take diamonds and put them into saw blades so it can cut through things. Yeah, so diamond, if you look at the entropy table that's in your book, diamond at room temperature has an entropy of 2. 2 joules per mole, where everything else is like in the double digits. Or graphite, I think it's around 6, so it's close. Graphite's real ordered too, but yeah, diamond is the winner. Okay, now we're going to move into this idea of delta G. I'll just be quiet for a second. If you want to copy that down, go ahead, and then we'll connect.
I'm so sad.
What?
Picture of them in there. There's no picture. So sad.
Oh, Well, draw it.
Question mark. Whatever you call it, can you call it Gibby?
Gibby.
Be
Yeah, I could do that.
Bonnie
Oh
Jean.
yeah, yeah. What was the kid? Isn't that his name? The kid's name from iCarly?
Oh, yeah, Gibby.
Oh yeah, dude, the only episode I remember, there was only two. The one where Spencer makes that.
Katie, you're gonna get us totally
No,
off
I
topic.
just, it's gonna be really quick. It's the one
No,
where
it's not.
Spencer, it's the one where Spencer makes that art sculpture and he's just sitting there, like for hours. I cried. I remember.
See, look. Now everybody's gonna say, "Oh, wait, what about this?"
Oh, and
Yeah,
the
no.
Victoria's
Katie.
Flash of Light. Sorry. Yeah, it was a good one.
We wonder why we get on track.
Yeah.
More on track.
Here, all this time I thought it was me.
Scapegoat. It's actually
Gibbs came up with this before there was a Nobel Prize. He would have won a Nobel Prize for his work in thermodynamics. He's a super, super smart guy.
Yeah.
Do you remember yesterday we talked about how delta S of the universe, if it was positive, then a reaction is spontaneous, and that has a lot to do with this term right here. Those two are very closely related. In fact, on the next slide, I want to show you that how they kind of are really the same thing. This was not just developed out of the blue. Gibby didn't sit around thinking, I wonder how I could throw delta H in there so that we can have a spontaneous process too. No, it was all kind of derived through the same means. So let's take a look at a little simple derivation. How is delta G related to whether a reaction is spontaneous or not? We know that if the entropy of the universe increases, a reaction will be spontaneous, or a process will be. What about delta G? Did you learn about delta G in Chem 1? I don't remember talking about it last year.
For it. Like you didn't have us like solve
Yeah.
Yeah.
Used to spend a lot more time on it, and this year we didn't. Last year we didn't do much. Okay. So this is what we're starting with. The delta S in the Gibbs free energy equation is of the system. It always is. Remember, I told you this yesterday. If I am talking about the surroundings, it'll say delta S of the surroundings. Otherwise, if you don't see a subscript on delta S, it means for the system, no matter what. Okay, so if I take the Gibbs free energy equation, divide out to T, just do this. Delta G over T equals delta H over T minus T delta S over T. So just divide it through by T. And what do you see?
Negative.
Uh-huh. I see them canceling. The T's canceling there. Remember that it's delta S of the system. I want you to keep that in mind. What do you see here in this term? Something familiar?
Of the,
Yes. We learned yesterday that the delta S of the surroundings is negative delta H over T. Yeah?
yeah.
Oh, I put delta T over T. All right. So that means that this thing right here is negative delta S of the surroundings.
Yeah,
Okay, so I'm just going to extend this a little bit in a different color. The left side of the equation is not, we can't really do anything with that yet, but this delta H over T is negative delta S of the surroundings. And that's minus delta S of the system. I'll go ahead and put the SYS down there as a subscript. Okay, now we're all very good at math. And I've got a negative term here, and it's being added to a negative term here. So, yes, you are good at math.
Yeah, that's true.
That's negative 1. I'm going to just pull the negative sign out of these two terms, and it's going to look like this. Delta S of the surroundings. Oh, man. I wish I could write neater on this. Plus delta S of the system. Sorry. What do you see right here? Delta S of the surroundings plus delta S of the system.
Delta S.
Of the universe. That's right. So, I was a little bit forward there. That's what I replaced that with in the surroundings. Whoops. Just do that. Go away. Yeah, delta S system plus delta S of the surroundings is the same as delta S in the universe. So this, what have I just done here? Here's where we're at. Delta G over T equals negative delta S of surroundings plus delta S of the system. Now this thing right here is the delta S of the universe. So that means what? For a spontaneous reaction, the delta S of the universe must be greater than 0, must be positive. We must increase the entropy of the universe. So what does that say about delta G? If we have a spontaneous reaction and this term is positive, what does that mean about the sign on delta G? Has to be negative, because this term is always positive. It's the Kelvin temperature. It's always positive. So if a reaction is spontaneous, the delta G is negative. This thing right here is one of the foundational, most important things that we'll do in this course.
What does delta G even mean?
It is, well, it's this. It's the combination of the enthalpy change with the entropy change.
So the shorter with what?
What's that?
It's like
Well, when we're considering these two things, delta G, it's called Gibbs free energy. What they mean is the energy available in a reaction for doing work. How much energy is available for doing work? So like when you had gasoline exploding in the cylinder of a car, that change has a certain delta G associated with it, which can be translated into how much work that reaction can do. That's what delta G is.
Wait, so it's not just
I don't know
like,
what that is.
so it's not just some like random.
No, it's not random at all. No. So there were two principles in the last week or so. Delta G is one of them. One of the very foundational, fundamental things we have to understand in here. The other thing is from about a week ago when I told you that if bonds are broken, you have to put energy in. If bonds are formed, energy is given off. That's very important to understand too. You know, you've only had this course for, 11 weeks or so, I'm just telling you, those two things, you haven't really seen them much until now. But as we go through the year, we're going to hang on to those two principles because they will allow us to do much more. All right. The next thing, oops, I went too far. The next thing is very similar to the reading quiz that we did yesterday. And I talked about this. I showed you the contrast between number 2 on your reading quiz, which gave us I don't remember what yours was. Yours was,
H2O liquid.
yeah, freezing water at negative 20 degrees? Or were you positive 20 degrees? You were negative. In my other hour, it was positive, and I think you saw that one was spontaneous melting and the other one was not. Let's take a look at this too. We're not doing delta S's only, we're going to do delta G. So the melting of ice, solid water changing to liquid water, the delta H and delta S are the same as they were in the reading quiz. It says right here that delta H is unfavorable. The positive sign on delta H is unfavorable. What the heck do you mean by that? And the positive delta S is favorable. What? They're both positive. How can one be unfavorable and one be favorable? What? This is a big deal too. When we do heat exchange, a reaction and heat can either be given off or taken in. If the delta H is positive, that means the system has to take energy in. Heat is coming in from the surroundings. Matter has a tendency of trying to get rid of energy that it has stored in it. So to have a reaction take in energy is not favorable. Things tend to go on their own if they can get rid of energy. So it's true that when you have a reaction that has a positive delta H, that positive delta H means that the reaction is going to kind of resist happening because it's got to take in energy.